This is a stress strain graph question. I'm going to go right through all of the questions from 3 to 8. So engineers are testing steel cables for use in a lift or an elevator. The first cable they test is sample X, and it has a length, an original length of 10 meters when unstretched. And here it is here, a graph of, they apply a stress to it, and this is the strain that they measure. So remember, when they're applying a stress, obviously they're applying a force, they're pulling on it, and they're seeing how much does it strain. So if they pull on it and apply a stress at 300, it stretches, or its strain is 1.5 by 10 to the minus 3. Make sure when you're reading off this graph, you don't forget the units. This is in megapascals or by 10 to the 6. So this is not 600, it's 600 by 10 to the 6. And this is by 10 to the minus 3. So this isn't 5, this is 5 by 10 to the minus 3. So make sure you remember all of the units when we go to do our calculations. Right, which of the following gives the best value for Young's modulus? So if you look on your notes or your cheat sheet, you've written down Young's modulus is the gradient of the straight section. Another name for the straight section is the elastic region. This is this section here. So we've got to find the gradient of that, the rise over run. Because it goes through 0, we only need to pick one of the points. So I'm going to pick this point up here, right at the end. And how much does it rise? It goes from 0 to 400. It rises by 400. By 10 to the 6 to 10. Remember, by 10 to the 6. Here we've got the 10 to the 6. And it goes from 0 to 2 by 10 to the minus 3. If you do that calculation, 400 divided by 2 is 200, and 10 to the 6 over 10 to the minus 3 is 10 to the 9. And you put those zeros into there, you get 10 to the 11. 2 by 10 to the 11. The sample of the cable breaks at point F, so it breaks here. When the force is this, force. Which of the following gives the best estimate of the cross-sectional area? Okay, so we're getting given force, so we have to calculate area. What's the thing that relates those two together? It's stress equals force divided by area. That symbol there is just stress. So if I want to find area, I can rearrange this equation, and I want to rearrange it, it'll become A equals force over stress. We know what the force is, 1.8 by 10 to the 5. What the heck is the stress? Well, they tell us we're talking about when it breaks at this point F. So we can actually read the stress off the graph. So remember, here it says stress, and this is stress. Point F, what's the stress? If we read it off the graph, here we are, it's about 450 by 10 to the 6. So 450 by 10 to the 6. And we do that on our calculator. And I've already done it. It comes out at 4 by 10 to the minus 4 meters squared. Right, which of the following is the best estimate of the length of the cable in the sample when it breaks? So when we start thinking of doing calculations on length, what I start thinking of is we've got to use strain. Strain equals change in length over original length. That's strain, this is original length. Right, we've got somewhere up here, we've got the original length, yep, cool. And we've also been given when it breaks, that's at point F. Here's where it breaks, here. So if we go like down here, we can read This is the strain. We can read the strain off, 4 by 10 to the minus 3. So we've got, from our graph, the strain, and we've got the original length. If we want to, we can calculate the change in length, which is going to be really helpful for this question. So we'll rearrange it to find the change in length. We get, that's what I want. Change in length equals strain times original length. So at the point where it breaks, the strain is 4 by 10 to the minus 3. And the original length is up here, 10 meters. That's 4 by 10 to the minus 2, or 0.04 meters. That's how much its length changes by. So if it started off at 10 meters, and it got bigger by 0.04 meters, the new length is equal to 10.04. If it started off at 10 meters and it got smaller by 0.04, the new length is equal to 9.06 meters. Now, the question is, if it got smaller by 0.04, it becomes that as 9.96 meters. The question is, did it get smaller or did it get bigger? Well, what are we doing to this material? We're testing steel cables for a lift. Okay, if we're thinking about here's a box for a lift, and here's the cables that hold the lift up. They're going to be put under tension. They're going to be stretched. So probably we're talking about the length of the cable getting bigger and bigger. So because it started off at 10, it would have been stretched by this amount. Instead it got smaller by this amount. So we're going to be looking at this as our answer. That's answer C. Alright, carrying on with this. On the next page, they need to test a different sample, Y, the different material, and here's X from our last one, and here's Y. Alright, in successive tests, cable Y is stretched to point P, here it is, then to Q, cable X is strength to R, and then to S. Which of these cables will not return to the original length? So the rule is, when something goes past its elastic limit, it won't return to its original size. Okay, it'll be permanently deformed. So here's the elastic limit here. Here's the elastic limit here. So if it goes to P, it'll go back to its original shape. If it goes to Q, that's just inside the elastic limit, it'll go back to original shape. R will go back to its original shape, but S won't. So which of these is likely will not return to the original length? And we've just found out it's only S. Comparing the materials on X and Y, which of the following best compares their stiffness and their toughness? Okay, so stiffness is the gradient. So if we look at this has a bigger gradient, Y has a bigger gradient than X. So Y is the stiffest. And toughness is area till breaking. Till breaking. Right. Here's breaking. If you did the area under this graph here, it would be all of these squares here. Whereas this one is way out over here. And if you worked out the area under this graph, there's a lot more squares to count. This has a bigger area under the graph till breaking, so sample X is the toughest. So X is toughest. Alright, which of these questions or answer satisfies that? X has greater stiffness, no. Y has greater stiffness, yes. And greater toughness than X, no. X has greater stiffness, no. Y has greater stiffness, yes, but lower toughness than X. Yep, that's our answer. Right, to test another cable Z, same material as X. So it's going to have the same graph as X. Alright, the sample has a stress of 300 megapascals, so they stress it to 300, they stress it to here. Which of the following gives the total energy stored in the cable at this stress? Alright, when we're looking for total energy in a stress strains graph, the way you work it out is area under graph times volume of sample. Times the volume of the sample. Right, so at 300 megapascals, let's work out the area. Here's 300 megapascals, here's the thing here, so this is the area we want to work out right here. What's this area here? What shape is it? Well, it's a triangle. There's two ways you can usually calculate the area under the graph. You can do it by shapes, which is the way I'm going to do it. The other way you can do it, which I'll do in, I might do in some other questions in another year, is count the squares. But I'm going to do the shape for now. So the shape of it is a triangle. The base is 1.5 by 10 to the minus 3. The height is 300 by 10 to the 6. So down here's our working area under graph over here. It's a triangle, so half base height, and that was a half times the base was 1.5 by 10 to the minus 3 by the height was 300 by 10 to the 6. If you do that in your calculator, you get 225 by 10 to the 3, and that is joules per meter cubed. It's the units working out the area under the stress strain graph. Alright, the volume of the sample. Volume, that equals the area of the sample times the length of it. And don't get this area here confused with the area under the graph we've just worked out. Okay, we're looking at the cross-sectional area here, and here's the length of it. These are the numbers that are going in here. So we've got 10 to the minus 4 by 10 meters, which equals 10 to the minus 3. So then area under graph times volume of the sample, you take this and you times it by this, and you get, if you put that in your calculator, you get 225.